routing meeting controls fine. Okay. Yes, so again we'll just recapitulate what we have learned during the first half of the day today. Okay. So I will remind you. I will remind you to the logistic map. Let me. Okay, so we'll start with again revising what we have learned so far. So currently we are discussing the simplest nonlinear map available in the literature of nonlinear dynamics. That is the logistic map. So R is a parameter and X prime is, or maybe better it is X n plus 1 is R xn 1 minus xn. Okay. So this is known as the logistic map. And we are trying to understand the dynamical behavior of this simple one-dimensional map. So first of all, this is a 1D map because there is only a one dimension, that is X, and X is a state variable. Okay, X is a state variable here. So X is a state variable which keeps on changing or which evolves. That is known as a state variable, right? Then we have R, that is known as a parameter of the map. We are interested in the long-term behavior of this map. We are interested in the of this map of the map as you vary as R varies, as parameter R is as R parameter varies. Okay, so that's our concept till now. And what we did, we took some discrete values of R. Okay, first we took, I will write the value of R here. First we took R equal to 0.7. Then we found that this is a long-term evolution. Then what happens on a long run of the system as you keep on iterating. So when we took R equal to 0.7, we got a fixed point. Okay, like it was always converging to 0. That is X star equals to 0. Okay, whatever you do, it was going back to 0. I hope you remember the curve that we plotted, X versus the number of iteration. We started from say 0.8, then slowly it decreased and it converged to 0. So this is the 0 part. So it kept on at 0 as you increase the number of iterations. Okay. Now what we did, we took say R equals to 3. Okay. There we saw that we are obtaining a period 2 orbit. What is a period 2 orbit? Say it is a set of say x1, x2, okay, such that when suppose this is f of xn, we can say. So what is f of xn? F of xn is R xn into 1 minus xn. Okay. So this is period 2, that is x1, x2, such that if it is a period 2 orbit, then f of x1 equals to x2 and f of x2 equals to x1. Okay, can you redefine this one? So if we consider f of x2 equals to x1, what is x2? X2 from this line is f of x1. Yes, and this is equals to x1, right? So f2 of x1 equals to x1. That means if you have 2 points, x1 and x2, it means that you start from one point and you iterate your map f, it goes to x2. And if you iterate your map f again, you will come back to x1. Okay, so like that, it is a period 2 orbit. So it will hop in between these 2 points only. So therefore, it is known as a period 2 orbit. Okay. What else next we saw? We saw that if you take this parameter 3.449, and we saw that yes, this is not trivial. You have to see the bifurcation diagram and all this. And you got this value, there it is period 4. And subsequent iterations, so if you increase more, 3.5644, you will get period, period 8 orbit. Okay. So on, if you keep on increasing, say 3.56, 44. Sorry, this should be 44. I missed it. 3.544. This is 5644. So you get period 16 and so on. And so on you go. Then at 3.8, we saw chaos. That means no repetition was happening. No repetitions were happening, right? That we saw in our program, in our code. Okay. So then we try to understand how this parameter R is affecting the long-term evolution of this one-dimensional map, a logistic map. So for that, what we do? Yes. So for that, what we do a clever data visualization technique that from the x-axis will be R. You select an initial point, say 0.7, and you select a final point, say 3.8. Okay. Now, for each value of R, okay, we are interested in what are the long-term evolution of the system as R. Okay. For that, what we do? We say that for each parameter set, okay, so this is the initial parameter set, initial, and this is the final parameter set, okay. In between that, if you want to know a very small changes in the parameter, you can 0, 1 change. It's up to you. The step size is up to you in your hands. So step size, select a step size for like say delta R, say it is 0.0001 maybe. That is fine enough. Okay. So next point will be 0.71, then 0.72, so on. Okay. Now, in order to understand this more clearly, what we do? We will compute the long-term evolution of the system at each of these parameter values. Say, let us take one parameter value. Say R equals to 0.7. Then you run the system, do the iteration, say x0, x1, so on, till x500. Okay, this is your last iteration. Then you take the last 100 points. Okay, why last 100 points? That means, yeah, that means what? Yeah, so that means that you take only last 100 points, that take x400 to x500 and plot it on y-axis. Okay, this is our idea. Why we plot only from 400 to 500? That means we are neglecting from first iteration to 400 iteration. Okay, that is a transient for us, and we are eliminating those. So you will get like some 100 points here for each R value. You will be having 100 points. Okay, so you can imagine how this diagram will look like. Okay, so how it looks like, that also we saw. So we had a code with us, and we found, yeah, I think it is not connected. Reconnect. Let us take the previous values, that is 2.5 to say 4 we had. Okay, and we run the program. So how many steps I have taken here? You can see I have taken a huge 10,000 steps. Can you see the R equals to R values is np.linspace, R min, R max, and 10,000. Since I have used 10,000 points in between on the x-axis and 10,000 parameter values, therefore you are seeing a very high quality bifurcation diagram. Okay, so it is still running. That's the reason it is still running. So you can see this was the bifurcation diagram. So what is happening? So for R equals to 0.7 and also later as you increase R 2.6 and so on, you are getting only 1 point. So those 100 points is just a single point value. So it is plotting only 1 point here. Then at this point, the qualitative behavior of the system changes. That means it gets doubled. So later you will come to know that this is a bifurcation, that is where fixed point to period 2 orbit starts getting existing, and this is a bifurcation, and it is a period doubling bifurcation. Okay, why it is period doubling bifurcation? From period 1 you are going to period 2. Okay, then again from period 2 you are going to period 4, then 8, then 16, 32, so on. Then above around 3.7, 3.57 or something, you see chaos. Chaos is denoted by the smudge. All right. So chaos is denoted by the smudge here. You can see. So this is a usual route. This happens with any nonlinear system you take, known as period doubling route to chaos. Why it is known as period doubling route to chaos? Because every time with increase in parameter, your period is doubling, and it is finally, is it doubling forever? No. There is a criticality at which it doubles up to say 64, 128, then it turns to chaos. Okay, so therefore it is a route to find period doubling route to chaos, and it occurs for a very simple map, just a quadratic Rx into 1 minus x. So you can see how the simplest nonlinear map can have such huge different dynamical behaviors. Okay. So let me take a screenshot of this. So why I took, I will tell you soon. Yeah. Yes. So this bifurcation diagram, this is known as a bifurcation diagram. More, if you go deep into the study, all right. So then what I told is then we learned about a Feigenbaum constant. Okay, what is that Feigenbaum constant? Feigenbaum constant is around 4.66. Okay, but how he came? So I told you the story of Feigenbaum also. Before that, let us see what it is. What this is called. This is known as usually the bifurcation diagram. Bifurcation diagram. Why this is known as a bifurcation diagram? Because for understanding the changes, qualitative changes or dynamical changes of this map, discrete map, with the variation of parameters. And through this, you are actually able to see different types of bifurcation. Okay. What kind of bifurcation? See, I told you, I will cover it later, but this is a change. This point is a change, something changing. Previously, it was a steady state. Now it is oscillating. You can see till here it was oscillating. Then at a later stage, period 2 orbit, it is oscillating, right? Period 2 is oscillating. So there is a qualitative change in the behavior. So such qualitative change in the behavior with the change in parameter R is known as bifurcation. So this point is a bifurcation point, okay, where period 1 orbit bifurcates to period 2. And since it is doubling, since it is getting doubled, it is known as a period doubling bifurcation. Okay. Since it is doubling, it is known as period doubling bifurcation. Then you will ask, how about this point? Yes, sure. So this point is again another period doubling point. Period doubling bifurcation again is occurring here. Okay. Again period doubling here, so on here, again, till chaos is reached. All right. So through this, you are able to, only by varying single parameter R, you are able to identify changes in this simple dynamical system. Okay. Therefore, it is known as a bifurcation diagram. If you want to be more into deeper, if you want to go more deeper, this is known as one bifurcation diagram. Because you are only changing a single parameter R. Yes, you are changing only single parameter R. Is there any other parameter you will change? No. So you are varying one parameter and you are generating this diagram. Therefore, it is known as a one parameter bifurcation diagram. Okay. Fine. Then Feigenbaum is a scientist, basic statistical physicist. So what he did is maps, this kind of nonlinear maps, and he got a pattern in this map. Okay, what is the pattern? So let me tell you. This one. So what he did, he ran the logistic map. He saw this kind of pattern, period doubling route to chaos. Then what he did, he thought that maybe I can take another map. So he took xn plus 1 is f of xn, that is sine pi of xn. Okay. So this is a nonlinear map. Okay, again, because sine is a nonlinear map. Okay, sine is a nonlinear function. So therefore he took sine function, and for that, say sine r sine xn or pi r sine xn, we introduce the parameters, and you change the parameter and get this plot again, similar plot. Then he got the similar kind of plot, same fixed point doubling to chaos. So then he got very surprised that maybe this is not only for only logistic map, this is for any one-dimensional map. Okay, to test his understanding, what he took lot of different maps, and he found. So this phenomena you can find in any one-dimensional nonlinear map. So what he did, he got curious and he started measuring things. So what he did, you can see the grid here. Let us take this grid. Okay, this is the grid point where period doubling occurs. Period 2 orbit is there. Yes, birth of period 2. We say birth of period 2 orbit starts. Then here, so again here you can see. Let's not worry about it here. So he took this distance. This is the distance where period 2 orbit exists, isn't it? Do you agree that this is the line segment I drew is the segment where period 2 orbit exists? Okay, only period 2 you can see. Next, what he took? Next, he took this area from here to this region. Okay, you got it? So similarly, he took, and these letters he represented as delta n, and this is say delta n plus 1, and so on. You can take it for different other periodic orbits. Then what it found is, if you do it time and you take the ratios of those two distances, delta n plus 1 by delta n, and for as you take for higher periodic orbits, then this number converges to a single constant 4.6, and this is known as a Feigenbaum constant. Feigenbaum universality constant. And this is true for any one-dimensional map you can take. Say you take this the sine map. For that also, you will get 4.66. Okay. So many researchers have said this, that this constant is same. The usefulness of this constant is same as pi is to circles. As pi is to circles, this number we say usually delta as 4.66, and delta is like the Feigenbaum constant. Okay, delta is the Feigenbaum constant. Fine. Okay, so yeah, good. Yeah. So then he later made some analogies to different statistical physics problems. Okay, and you know that many researchers, they study the quality of different metal surfaces under a like a X-ray microscope, or many there are TEM, like TEM I think, transmission electron microscope maybe. So using that microscope, it can actually it can show you the, if a metal which appears very smooth is actually broken somewhere inside at a micro, at a tiny level. Okay, so that what TEM does. Okay, so he in those kind of metals also fractal patterns are there. We will see when we are actually learning about fractals. So after this maps, we will go to fractals. Okay, how to generate fractals. Yeah, what are the different characteristics of fractals, and yeah, like that. So good. Already know Feigenbaum. He's a great scientist in the sense that he was very hardworking. Like he came to know that there is a pattern, but it is very difficult for someone to do something on this, something new. It is very difficult to do something new things. So therefore he started with this, and he came to know that yes, if he does like this for different one-dimensional maps, then get this constant. He tried to publish this to like in a very good journals and all, but around 1970s and all, so his paper got rejected 3 times. So without losing hope also, he published 2 of the papers based on this, only on this, in 1978 and 1983. Okay. was also a very nice person in the sense that science never sleeps and science never stops. So he usually wanders at night at his university, and yeah, the security people, they ask him, "Is he fine? Is he fine?" And also, yeah, he says, "Yes, I am thinking about a new problem or about this, what I will do in the next day." And he chose that time because that time is very peaceful. So even there is question, you should ask me the question, sir, why we will can take only horizontal lines? Why not vertical lines? Why not vertical lines? See this picture very carefully. See this picture very carefully. You will see that we can take also this distance and this distance, isn't it? Yes, then we can take the ratio of these distances also, and this distance again here. Okay, so you can tell maybe this is dn. Say this is dn. This is dn plus 1, so on. Then you should ask a question: can, if you take such a limit, can limit say to infinity dn plus 1, the width over dn converge to something? Length is converging to something. How about the width of this? How about the width of existence? The width is actually decreasing, isn't it? As you move, the width is keeping on decreasing. Yes. So actually, yes. And it actually converges to a number. That number is 2.5029. But yes, no one has still allotted a name to this yet, because it might be redundant, because you already found a universality constant for this horizontal. Then it might imply that since you are getting this universality constant, you can also get a constant if you consider this kind of distances. So now you saw how this structure is actually organized. It is not just organized randomly. Okay, every pattern you see is having some significance. Are you feeling that? Are you feeling? Yes. So yes. So therefore, any pattern you see, okay, what we did is later we found that indeed they are like fractal like structures. Okay. Okay. Uh, to the next step. Yeah, maybe I'll show you some new versions of it. Uh, yeah. So this was the plot here. Okay. Can you tell me like which region shall we see? Let us see a different region now. So there is a very nice region which I did not tell you previously. Okay. So if you see here, this is period 1 orbit, right? Always stay there. This is period 2 orbit. Okay. But suddenly it went to 4. Where is 3? Where is period 3? Can you identify period 3 here? Does it exist here? Where? Can you see period 3 orbit in this bifurcation diagram? Period 3 means at the point where? Can you show? Can you show? Come. Show. Through hand. Is now the periods between 1 and 2 are possible at this point. At this point. Huh, so period 1 is getting transition to period 2. This transition point only like all the in between period 1 to 2, what are the periods? Like all. Period is an integer, positive. Yeah. Like okay. Okay, can yeah. Okay. can you say to me like where is period 3 orbit? Huh? Where? No. No, see, I am talking about the things which are visible. What you are saying is when period 1 orbit is transiting to period 2 orbit, in while transiting, lot of things are possible. That's what you are saying, right? Yes, but that is a transient. We are not worried about transient. We are worried about long-term evolution. We are worried about long-term evolution. Yes. So therefore, all the things you are seeing, whatever points you are seeing on this diagram, are in this transients are eliminated. No transients are there. I will show you the effect of transient. That's a very good question. I will show you. I'll come to that. Remind me that I will show this figure with transient. Now this is without transient. I told you 500 iteration we will take. Only last 100 points we will plot here. First 400 are the transients we will eliminate. But that's a good question. What happens if you consider the transient? Yeah, we'll consider that. Fine. But I am asking period 1 is there, period 2 is there. So where is period 3? It is there. Think. Where is period? Okay. So what I am telling you is you can identify period 3 orbit here at this point. See my mouse cursor. Period 3 orbit is here. Why? 1, 2, and 3. Period 3. In order to visualize it properly, we can zoom in that region. Can you tell me, say 3.8 to 3.9? Okay, 3.8 to 3.9 sounds good. So let us zoom in that region. So, okay, fine. Let us run. Take some time to run, but yeah. We are generating a very high quality image. So yes, can you see now? It's a period 3 orbit. Okay, and what is more beautiful in this structure is, let me plot from 3.82 to 3.86. So, but anyway, you can visualize now that see the structure. Isn't this structure the same which you saw before? Yes. Now, if you zoom in, again you will see that kind of structure. So therefore, this bifurcation structure is a fractal-like structure. It keeps on self-repeating object. Okay. In that way, this is a fractal. And these curves you see here, they also play a role. Okay. All these are orienting here. All these are orienting here. These are known as Q curves. Q curves. So this is more advanced, which we will not read for now. But yes, many can ask questions that, sir, what is these things? What are these iterations? Still, why we see this? You can see that this simple map can exhibit such a striking complexity. Okay, and all these they merge here, and these are the Q curves. You can compute those Q curves. Okay, you can actually show that these Q curves are actually these curves here, and they actually intersect here. Okay, you can search on Google also Q curves in logistic. Fine. Let us go again to our study back. Okay, fine. Now now we will learn another concept here. I will move to another concept. So you can see this is the logistic map. It is a one hump map. Okay, there is one hump. Now what we are interested in is what is the form of the map near the origin 0, 0. Okay, let us zoom that map. Okay, you can see that it is very similar to y equals to x. Near 0, 0, it is very similar to y equals to x. How? See this point of the grid. It is 0.005. Again, it is 0.005. So it is a like y equals to x. Okay. So the logistic map at the point x equals to 0, near the point x equals to 0, behaves like a straight line. Okay. Therefore, keeping this in mind, we will study a topic here. I will discuss the main aspect of stability. We will come to the main aspect of stability here. Okay, so let us see what happens. Let us see what happens at x equals to 0. Okay. So before that, I will tell you one more thing. Yeah. Just find the graph of logistic map at x equals to 0, near x equals to 0, y equals to x, a straight line. Okay. Before that, now we will cover one of the most important topic in nonlinear dynamics, that is known as a fixed point. Okay, it's the simplest attractor of a dynamical system. Okay, and you might have heard about fixed point before also, any of your other topics. Okay. What is a fixed point? Any ideas? See, from logistic map in the morning, you must have known that it was coming from this and it was converging to 0. Okay, and then 0 was known as the fixed point. Okay. But then observe, like Rx 1 minus x, what happens to this if x equals to 0? It's going to 0. Yes. So there is some connection here. There is some connection. So here we want to elucidate that in deep. What is a fixed point, like standard definition, and then we will move to more attractors. So in order to move towards chaotic attractors, different attractors of a dynamical system, we will first study the simplest attractor, that is the fixed point. Okay. What is a fixed point? So this is the definition. Say a point x star, okay, is said to be a fixed point. Is said to be a fixed point. Fixed point of what? Of a particular map. Of a map. Okay, of a discrete map. Of a map F. Okay, if f of x star is equals to x star. This is just not a mathematical statement. You can visualize this. How? If you have a point x star and you have another point x star, f of x star, okay, what he is saying is those two are the same. Okay, that means if you iterate x star again, you will land back to that same point again. If you start from a fixed point x star and you iterate the map again, you will land to the same point again. That is a fixed point. Okay, so therefore, if you want to find a fixed point of a discrete map, you have to evaluate f of x star equals to x star. Okay, and x star is known as the fixed point of the map. Right. And what is the orbit of the fixed point? What is the orbit of fixed point? Orbit of any point we saw in the morning is equal to x star, then the iterate of x star, okay, then again the second iterate of x star, so on. Then the third iterate, you keep on iterating and store those points in a set, and that is known as the orbit. This is known as the orbit of x star. Yes. But what is this point actually? This is x star. Fine. What is f of x star? X star. What is f2 of x star? Again x star. Why? Because this is f of x star, and this is f of x star is x star. So f of x star again, and f of x star is again x star. Okay. So what you are getting here is actually a singleton set. Only one point is there in that set, isn't it? And that is the orbit of the fixed point. So therefore you can see, therefore why you got a single point in the bifurcation diagram for a fixed point. Okay. There is graphical interpretation of this. This is a bit of mathematical way, but graphically, how can you imagine this? Graphically, how can we imagine the fixed point? Note, x star equals to x star, right? So if you plot, so it is the intersection, the fixed point is the intersection of two curves, that is y equals to fx and y equals to x. Is that true? Do you think? See, f of x star is equal to x star means the fixed point you will get. But you can imagine this equation as the intersection of two curves, no? Y equals to fx and y equals to x. This is same as saying f of x equals to x. So this is another concept. Graphically also you can imagine how the fixed point looks like. Okay. Now can any map have a fixed point? Or do there exist map which doesn't have a fixed point? Can any map have a fixed point? What do you think? Give an example. If you think it is yes, give an example. If you think no, then give an example. Graphically, you can imagine. Graphically, you can imagine that I told fixed point is the intersection of the curve y equals to fx and y equals to x. Okay, y equals to fx we don't know. That can be any other shape of the curve. But y equals to x definitely you know. Yes. So let us draw y equals to x. This is y equals to x. Okay. Now, if the curve y equals to fx intersects this y equals to x, then you have a fixed point. Yes. What if I make a curve like that, it never intersects with y equals to x? Then it never have a fixed point. And which curve can never intersect y equals to x? Yes, anything which is parallel to y equals to x can never intersect y equals to x. So you can never have the fixed point. So therefore, take any line, any function which is parallel. Okay, any function you take which is parallel to y equals to x. Okay, that map will never have a fixed point. For example, think fx x plus 1. That means I am saying xn plus 1 equals to xn plus 1. This map can never have a fixed point. Why? Because the slope is 1. It is this y equals to x slope is also 1. Y equals to x plus 1 and y equals to x are parallel to each other. So they don't intersect. So no intersection. Yes, implies no fixed point. This could be concept. So that means there exist maps, discrete maps, which doesn't have a fixed. Okay. Got that idea? Yes. So in dynamical systems, in nonlinear dynamics, in dynamical systems in nonlinear dynamics, one of the main objectives of the study, okay, one of the main objectives of the study is to deduce the stability of the fixed point of the attractors, or maybe I will tell the fixed point. That would be good. Yes, stability of the fixed point. Okay, fine. Now let us come back to our previous concept. That means at x equals to 0 origin, our logistic map here, if you zoom in this part, straight line y equals to x that we saw using Desmos. Okay. Now, without going into detail into the stability, I will just show to you how graphically you can analyze the stability of a fixed point. Fixed point can be stable, unstable also. Okay, what is stable means? What does stable means? If you have a fixed point here, say here, 0. Suppose 0 is a fixed point, then any neighbor point you choose using condition, the future iterates will converge to these points. Okay, the future iterates of this will converge to this point. Okay, then it is a stable fixed point. And if it is a stable fixed point, you can see in the bifurcation diagram. So in this bifurcation diagram, this fixed point is stable, and therefore you are seeing a black color line. Okay, If it is unstable, you can never find it. You have to use sophisticated root finding methods to find it. Okay. Now, before going there, I will tell you. Yes. Yeah. Now the logistic map, if you see xn plus 1 is r into xn into 1 minus xn. Okay. If you see 0 is always a fixed point. Why? Hmm? 0 is always a fixed point, is it? Why? Here you can see that if you draw y equals to x, then it will be, it will cross here also, and it will cross at some other point also. Okay. So 0 is one of the fixed point. But if you want to solve for the fixed point, what you will do? F of x star equals to x star. Yes, and this is your f of x, isn't it? So r x star into 1 minus x star equals to x star. So x star I will keep common. So r minus r x star minus 1, right? Equals to 0. Fine. Is this okay? So from here you get, yes, 1 x star is 0, x1 star is 0. Another is, say another fixed point x2 star is, yes, fine. So these are the two fixed points of the tick map. Okay. Now, stable. Usually, if you have more than one fixed point, only out of them, only one fixed point is usually stable. It's very uncommon to have like, okay. So out of these two, one is stable, one is unstable. Okay, but which one is stable? Okay. So therefore, it depends. If you see, the stability depends on the parameter r. But how? Today, we will not discuss in deep into stability, but through graphical approach, I just want to tell you the concept of stability. Okay. So again, we want to analyze the stability of x star equals to 0. So look nearby x star equals to 0. And nearby x star equals to 0, you know, your map looks like the straight line y equals to x, like passes through origin. Yes. Fine. Okay. Got that concept? So you can say near x star equals to 0, the map behaves like far away, but only near x star equals to 0. It behaves like xn plus 1 is rxn. Okay. Only I'm taking the linear part passing through the origin. So there is no quadratic non-linearity here. Fine. Understood? No. So what I'm saying here is, if you, this is the logistic map, that is the hump. Okay. I am only looking nearby the origin. Nearby the origin, it looks like a straight line passing through the origin. Okay. So your logistic map is Rx minus Rx square. So if it is linear, we will take only the linear part. No need of the quadratic part. Okay, because nearby this only I am seeing, not away. So therefore, you can approximate, not equal, approximate xn plus 1 is Rxn. Okay. Now we go to the first class. I told you xn plus 1 is Axn. Yes. And I told you how the iterates are moving. Halim also gave one example, a equal to 7, and how, yeah. So it is like that map. Okay. Now, what is x1? You start from x0, then x1 is Rx0. x2 is R square x0. Yes. x3 is R cube x0. So on. And xn is R to the power n x0. Okay. Now, if this is an orbit of the trajectory, orbit of the starting from x0. Fine. Okay. Are everyone on the same page? Now I'm saying, if mod r is less than 1, in between -1 to 1, then what is r to the power n go to as n tends to infinity? That means long-term evolution. Why I'm considering n tends to infinity? I'm considering the long-term evolution with time, with the number of iteration. So if n tends to infinity and r is in between -1 to 1, then what is r to the power n? It will approach 0. Yes. And if mod r is greater than 1, then this quantity r to the power n will increase every time you square it, cube it, fourth it. so on, and it will go to infinity as n tends to infinity. Yes. Now, based on that, you tell me, out of these two cases, which will be favorable to make x star equal to 0 stable? First one. Yes, why? Because it is going to 0. And what is 0? 0 is the fixed point. Okay, you start from anywhere. If your parameter is in between -1 to 1, then your future iterates, that is xn, is going towards 0. And 0 is the fixed point of the map. 0 is the fixed point of the map. So therefore, it is stable. Stable, right? Now, if you see this, your mod r is greater than 1. Now, whatever you do, it is going away from 0. It is going away from 0, like iterating away from 0 and going towards infinity. Okay, so therefore, this is unstable. Okay. Stable in the case, you can think of it as, I will give you, those who are not that much aware for stability, I will give you one example. This is a pendulum, okay? This is just a pendulum here. What you do, this is actually the fixed point of the pendulum. This is the fixed state or rest state of the pendulum. Why? Why? Because it's a stable state. Why it's a stable state? What you do is just take a small perturbation, release it back. Will it be going this side? No, it will be coming back to its original state. Same again, if you go to the other release again, it is not going to go this side. It will be coming towards the rest state. In that sense, you can say whatever disturbance you make, it is coming to this state. So this state is a stable state. Can you identify an unstable state in the pendulum? Unstable state of the pendulum? That means if it goes away from that point, of course, this is a string, okay? This is a string. You can also do the pendulum like this, isn't it? You can take it on the upside and release it. Just a small perturbation you do and release. Will it go this side? No. Due to gravity, it will come back here, down. If it is coming back down, that means it is coming to the first state. So this is a stable state, okay? And this is your unstable state. So same example here only, we are seeing that if your parameter r is in between -1 and 1, okay, the future iterates are converging to 0 and 0 is a fixed point. Okay, so therefore in that case, 0 fixed point is, if your mod r is greater than 1, then it is not coming near to the 0 fixed point, rather moving away from that 0, right? Going towards infinity. Therefore, it is unstable fixed point. Okay. This is just the graphical interpretation. Later, I will tell you why R is there. Why? What is the speciality in R? Why only R came into picture? Okay. So later, slowly, we are revealing the case. Okay. Like the detectives, we reveal the case slowly. So you will come to know why these things are happening like that. So I'm not giving you the full picture at once. So I'm giving you small doses. So you will appreciate it later in the next class. So next class will be important in the sense that we will be learning about different types of fixed point, how to find them, is there a condition, mathematical condition through which we can find the fixed point to be stable, unstable. Okay. And yeah, some more details we can look. But one more thing I will tell you, stability of the fixed point depends on the derivative of the function. Here, derivative of the function. Okay, this is a one-dimensional function, so your derivative of it. Okay, if you take more than 2 dimensions, then what numerical method people can tell? If you take more than 1 dimensions, then you can't take a derivative. Derivative concept goes, partial derivative concept comes because more than one variable. Okay, in those Jacobian matrix and all those comes. Okay? It's very useful in machine learning also. Hessian, similar to Hessian. So if you learn here also, it will be helpful in DL. Okay. So yeah. So next class we will discuss two main things.